In this video, in section 6.3, we're going to talk about geometric settings and finding probabilities within geometric random variables. So, the pass the pigs example from the beginning of the section we read about during class, the idea was you rolled until you got what's called a pig out, or you got a certain set of numbers in the die. And when you're counting the number of times it takes to be some success or a failure in that case, you're counting in a geometric setting. The number of trials is not fixed beforehand. You're deciding based on how many times it takes you to be successful. So an example could be rolling a pair of dice until you get doubles, similar to like a Monopoly game. You count how many times it takes you to roll a pair of doubles. In basketball, attempting a three-point shot until you make one. Keep placing a $1 bet on number 15 in roulette until you win. So in all these settings, you stop counting once you are successful. This is, contrast that with binomial random variables where you actually set a number of trials and you count how many times the person or the thing is successful. So in a geometric setting, not geometry setting, geometric setting, we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability of P of success must be the same. So number of trials until you are successful, and then each trial, the probability of success must remain the same. And they're all independent of each other. So a geometric random variable, possible values are going to be 1, 2, 3, and so on. There is no 0 here. And that makes sense because it takes you at least one turn or one trial to be successful at something. So you can't have a 0 in a geometric distribution. It is 1 and greater than 1. Probability of success is the only parameter, P. We don't have n like with binomial. We're not choosing the number of trials before we start. All right, the probability formula. It's going to be a little bit different than the binomial random formula, binomial random variable probability formula. So we're going to use y just to differentiate it. You find this by taking the probability of failure, 1 minus p, raise it to k minus 1 power, times p. So this is because there's only one success with geometric. So whatever number you get, k, there's always only one success. That one success is preceded by k minus 1 failures. So if you have 10 trials you have to go through before you're successful, you have 9 failures preceding the one success, and 9 and 1 makes 10. There is no combination or like in the binomial probability formula, there's no coefficient for the probability because you're not arranging the one success in different spots. The one success will always be the final trial. They're never going to have the first trial success and you keep going. In geometric, you stop once you're successful. So there's only one way to get this probability, unlike with binomial, where you can actually arrange the successes in a bunch of different ways, depending on the n and k values. In the TI-84, if you're looking for the commands, there are 2, just like with binomial, under the var distribution menu. Only 2 parameter or 2 numbers typed in though, probability of success, and then k is the number of trials. That'll get you exactly x equals k. And then they have a cumulative one as well, CDF, type in probability, k, and that'll get you less than or equal to k. That's your cumulative option. So you can use either one of those or both of them in conjunction to find certain probabilities. All right, let's go through an example. Your parents determine the number of hours you must complete chores during the week by playing a chance game. You have to guess a day of the week, 1 through 7, and your parents use a random number generator to pick a day. If you guess correctly the first time, then you only complete 1 hour of chores for the week. If you guess wrong, then you must complete the process again. If you are successful in the second guess, then you will complete 2 hours of chores. If not, then we complete the process again until you are successful. Define the random variable y as the number of trials it takes to correctly match the chosen day. So, if you get it right the first time, 1 trial, you get 1 hour of chores. If it takes you 2 times, you get 2 hours, and so on. So the number of trials is equal to the number of hours of chores you get. So So this says, find the probability of you getting exactly 5 hours of chores for the week. So 5 hours of chores means you needed 5 trials, and that's K. So what's the probability of Y equal to 5? Well, we need to have the probability of success, and that's it. So the probability of success here is 1 out of 7 because there are 7 days. You're choosing 1, and your parents are choosing 1 using a random number generator. So that's your probability of success. So that means that 1 minus P, your probability of failure, is 6/7. Okay? And we know it's geometric because the trials are independent. The probability of success is always the same. And you count the number until you are successful. So, using the formula from above, we're going to do 6/7 raised to the power of 4 times 1/7. And just to repeat here, if there are 5 trials, that's 4 failures ending with 1 success. So the probability of failure, 6/7 raised to the power of how many failures there actually are, times the one probability or 1 trial with the probability of success is 1/7. When you calculate that, you get 7.1% chance of getting exactly 5 hours of chores. What if we wanted to find the probability of Y less than 5? Interpret this in the context of the problem. So the probability of Y less than 5, there's a few different ways you can do this. You could do this way. Find all the probabilities that are actually less than 5. So that's 1, 2, 3, and 4. That's 4 terms you have to calculate, and that might be a little bit much. Your other option is to use your graphing calculator. The problem is that your calculator does not do less than. It does less than or equal to. So here's one option. If you know it's a geometric random variable, you know it's discrete. There's no number in between 4 and 5. So the probability of Y less than 5 is equal to the probability of Y less than or equal to 4. Because 4 is the next number before 5. There's no 4.5 or 4.8. It's discrete. So you can use your calculator to find this. And going through the menus, you could do that and you get 46.02%. And you have a 46.02% chance that you get less than 5 hours of chores for the week. The important part here is that this calculator that you're using does not compute strict less than, but it does do less than or equal to. And because this is a discrete random variable, you can use 4 instead of 5 here, and it's going to be the same exact probability. Looking at the distribution of this geometric random variable, the geometric distribution, you'll notice that there's a gradual decrease in the height of the bars as you increase the number of trials or number of picks required. The shape of this is skewed right. The center is going to be 7, which is the mean. And we'll talk about that down below. And the spread here, sigma y, is equal to 6.48. We are not going to do that in this class. So this is for an advanced stats class. We're not going to talk about how to find the standard deviation of a geometric random variable. What is important is that this shape comes from the fact that each bar that to the right is 6/7 the bar to the left. So if you were to multiply this height or probability by 6/7, you get the next bar. Multiply by 6/7, you get the next bar, and so on and so on. And that repeated multiplication makes it look like an exponential curve here. And actually, same thing with these values that are on the heights of the bars. You multiply this one by 6/7, you get the next probability, and so on all the way down the line. And this goes on forever, even though the probabilities get very, very small. It is infinite. Okay. Finding the mean or expected value of a geometric random variable. Again, this only works for geometric. If you want to find the average number of trials it takes for a person to be successful in a geometric setting, you simply do 1 divided by the probability of success. And it's just that simple. So for example, if you wanted to find the probability of getting a 5, or the average number of times it would take to get a 5 on a roll of a die, 1/6 for probability. So on average, it would take 6 times for you to roll the die and get a single 5. So if you were looking at this equation, mu(y), you would do 1 divided by 1/6. And if you wanted to multiply both of those by 6, top and bottom, what happens here is that the 6 times 1/6 is 1. 6 times 1 is 6. It would take you on average 6 trials to be successful there. So in Monopoly, a person can get out of jail if they roll doubles within 3 rolls. Find the probability this happens. Well, we know this is geometric, so we're counting how many times until we are successful. So y is less than or equal to 3. And when you use your calculator here, using p equals 1/6, you find out that it's 42.13%. And this makes sense because that's less than likely that you're going to be getting doubles within those 3 turns. On average, how long would it take you to get doubles? Well, what's the probability of getting doubles? It's 1/6. So 1 divided by 1/6 yields you 6 trials on average. And because they only gave you 3, it makes sense that you don't always get, or more likely than not, you don't get out of jail the first time, or even second time or third time. You must pay that penalty and leave like everybody or most people do. But if you are lucky enough to get within 3 trials, it just shows you that the probability is not in your favor.